Okay, now I will repeat very shortly the last 2 or 3 slides, and then I try to go ahead. Nevertheless, the concepts are always more or less similar. I will insist again on the convexity, not convexity of the optimization problem. And in particular, we will see today the not convexity. What is the meaning of this? No? We will see very well that we cannot apply directly the method which I presented until now. Because the method which I presented until now is based, where is it? I hope that I share, because today I worked all day long with Teams, and in Teams very often I would like to say it's easy because I don't need to to share every time to change the sharing every time which I change the window. I mean, I can share directly the screen here. But nevertheless, Zoom, the advantage, in my opinion, is more stable. No? Okay, I hope that you can see. Do you remember last time we have seen and we applied this solution? Here I didn't insist on this picture here, but look nevertheless at the orthogonality between this vector here, or better to say, at the difference between this vector here and this vector here. Basically, if this is the error between the real measurements and its approximating a vector on the plane with dimension n+1. Why dimension n+1? Because we have n+1 coefficients. Yeah.
Sorry, I have a question. I missed the last lecture and I tried to find the video on YouTube, and I'm not sure if I found the right one. If you say you have a similar course, there was something about the mechanical system and the car and the friction.
So it's not this one.
This is not the right one.
If you want, I would like to proceed. So I can send you the address of this course, so you cannot make mistakes. It's in a plain list with the name. If you want, I can share now if I'm able to do directly now in the chat. But go ahead with your question.
That was basically the question. I think I got the wrong video.
Let me see. Let me see now if I find. I think I'm inside. No, I'm connected or not. Ah, no. I have to do. Should I do now or I can proceed? The best way if I send later in my study to everybody. Yeah, because now probably I need time to look where is the playing list. Yeah. But if you find a video with a car, it probably is in a different course.
Yeah, but it was roughly the topic, so I thought maybe we just make some progress. And
I don't remember. It could be that it's similar, but there is a course on optimization in which we have some parts, some overlapping parts, because we are speaking about optimization now. But I don't remember that I considered in a car. But anyway, I have also a message here. Yeah. CB lecture 01, but the idea is a plain list, basically in which we have lecture 1, lecture 2, lecture 3. If you look, but I need time because let me go ahead with the lecture. I will send you at the end of the lecture. Otherwise, I cannot concentrate of, let me say, more important thing, even though it's important to have the material. But I think at this moment you don't need. But of course, it is better if I send you. Look, we have an orthogonality between the error, between the vector y and the vector, let me say, y hat. Please pay attention. This point here, I didn't put any elements because I don't want to. What is the origin? What is the origin? Yeah, because I don't want to go in depth on this because it's quite difficult. Think about y mean value, but I don't want to go in depth because mathematically it's a little bit more complicated. Do you remember I told you about, excuse me, we concluded here this equation in which SST is defined, let me see what is the definition here. It's quite for finite measurements. It's basically the variance multiplied by m minus 1. It's basically if you think about this picture here, now we can understand this sentence y hat, but mathematically at this moment I need too much time. Just flesh out the concept. It's this basically is if you think about your knowledge in statistics, it's something related. If you have a finite number of measurements, is related to the statistics, to the variance, which is one of the most important. After the mean value is the most important, statistic parameter. Probably variance, mean value. I don't need to repeat. Just fix the idea. Then we have this SSE. It is basically is what I told you until now. It's related to the least square. We optimized exactly this, if you remember. Here is also interesting because is nevertheless a residual. If you think, let me say, it's in a statistical parameter, because we have here basically the mean value. Here is basically the error. Look, if you want to interpret it geometrically, if you think about here y overline the mean value, this difference, this error is SSE. And this here is SSR. I don't know if it's visible. Think about here y overline. I don't clarify why and so on because I need too much time. But this difference here, the error, is exactly SSE. And this here is SSR. This means, you remember last time I told you that we can consider nevertheless valid this equation here, which can be a possible parameter, R squared, which came from this equation here. If I divided everything by SST, I will write this form here, or this equation here, in this form here. And you remember, I told you now an interesting interpretation. The data which I have, or a characteristic of the data, the variance, can be seen split in two parts. One, SSE, which represent basically, remember, the deterministic error. And this SSR, which represent the statistical one. They are orthogonal, therefore, we can say if we consider this point here, y overline, the mean value, valid in the sense. Why is it important, nevertheless, this equation? Because do you remember, we can realize, also didactically, as I told you last time, that increasing the order of the polynomial. For instance, in this elementary case, starting from 0 and end up in n equal 1, n equal 0, we have this expression here, n equal 1, we have this expression is the line here. We have the r square is 0 in this case. Why that? Because in this case, SSE is equal SST. Why that? Do you remember last time I told you, let me repeat. Because in this case, we have that, let me show you here better, that this y I hat, the regressor, is exactly y over line, because I approximate the point with their mean value. This means here is 1. This means r square is equal 0, meaning in this case, in this second approach, we have the maximal deterministic error, but the minimal stochastic one, because cannot be less than 0 SSR. Cannot be less than 0 because if you look at the definition, for instance, here, cannot be negative. In this case here, we have exactly the contrary, let me say, because in this case here, we meet all points. Do you remember? SSE is equal 0, because the error is exactly 0. In this picture here, this means that this hyperplane includes the vector y. This means this distance here will be reduced to 0. Again, in this case, we have the minimal deterministic error, but the maximal one, because again, SST is fixed. It's one of the minimum, the other is the maximum. I don't want really to go in depth on this because we will see that we will use another parameter, another indicator, which allows to optimize n, because here, what happens here? It seems, I don't have the demonstration here, I don't want to do, it seems that with respect to n, this r squared is not so a good parameter, it's not adequate to calculate n. Why that? Because it's not a demonstration, but we can see increasing n, r squared is increasing. In this case, between 0 and 1, but I can, but I don't want, I really a little bit difficult. It's not difficult, but it's boring. Believe me that r squared is a monotonic function with respect to n. This, as I told you many times, even a function indicator. If this is the cost function, if the cost function is a monotonic function, cannot be used to optimize, in particular n, because it's monotonic with respect to n. Let me say if I forgot to say something. Okay. Okay, this I commented last time. Basically, as I told you, this r square, we don't accept value close to 1 because of the overfitting. I mean, you remember I told you that the data, at the end I concluded with this sense, the data reflects the phenomenon, but is not the phenomenon, because inside we have errors. Think about our original sentence. Our processes are affected by statistical and deterministic error. Exactly this idea. The idea is to minimize both the deterministic and the stochastic one. If we assume that the reality is affected by error, paradoxically, do you remember last time I told you the reality, the true, is in the form of error? Do you remember philosophically I concluded this? It's interesting to say a little, it's a challenge, but don't tell you outside this room. But in any case, the true is in a form of error in this context makes sense because what we can assume as the true is the value the true. Again, for us, true doesn't mean anything. But in any case, we have a value. Look at this. We have a values. And the value, the measurements, are affected by two kinds of errors in our conception. The idea, in order to get our pseudo-true, is to minimize both. What we can obtain at the end of the course, and a representation of the phenomenology, any kind of phenomenology. With this representation, we can say this is the best representation which minimize errors in terms of statistical and stochastical error in accordance with the cost function. In accordance with the cost function. If the cost function changes, we cannot, we have to recalculate everything. Example, do you remember last time I told you, if I say I am the best professor, it's not. But if I say I am the best professor because I am the highest index, we have also cost function to measure the impact factor, it's not my case, of publications. This means knowledge which we disseminate, but with respect to something. Let me see if I forgot to say something. Yeah, here a little bit of this sentence I told you, the R square is between 0 and 1 cannot be less than 0 because all elements in these equations are square. Cannot more than 1 for the same reason, because SSE cannot be negative, SST cannot be negative. This means cannot be more than 1. The last sentence can be justified. Think about that. If you think about that, R square is basically SSR divided SST, and SST represents somehow the variance or the variation. Because the variance in some books is related to the infinite number. Variation is better, no? Look at the definition. It's too difficult what I am saying? Too boring? Yeah. No. It's okay. For engineer, probably it's boring. For you, it's boring. But I try to present another point of view too. If you think about SSE, but please, you can answer also the true, even though in our context the true does not exist. But you can say also, it's boring. No problem. Look here. This is something related to the variance, even though in some books we consider the variance if m tend to infinite. But the variation, I can say, because it's related, each real point is related to the, let me say, the mean value of the point. It is, if you think about the sentence, it's clear now that if I have a value 0,8, that means that this variation cover almost 80%, let me say quickly, because we can see exactly that is the portion of SST. If SSR is equal SST, we have exactly R square equal 1. Basically, the points are compressed in this line. Think about this a little bit. Why we don't use this? We don't use this because we cannot say what is good, what is bad, for different reasons. First of all, if I tend to 1, as I told you, I don't consider errors in the point. Therefore, do you remember before I told you this? We have the minimal deterministic error, but the maximal stochastic one. This means if I consider value around 1 very good for my, let me say, optimization, I assume that the points, the measurements, tell us the truth. But we cannot assume this. And this, of course, is related to n, because here I can choose between this approximation and this one. Of course, I can consider also uh, square model up to 3, up to 2. But of course, typically we don't do because these all models, these models meet nevertheless all point. We don't want to do that. Let me go ahead now. Do you remember we introduced this together? This possible variation is not the unique one, is a variation which allow to say uh, that the new cost function, R square adjusted, I adjust a little bit SSE divided SST. This variation, the possible variation, allows me to say that now R square adjusted, it is not, cannot necessarily be monotonic with respect to n. Because if p is n plus 1, exactly the number of coefficients, start increasing n, you remember, I can demonstrate, I didn't do, that SSE is decreasing. But in the meantime, I will decrease also the denominator because m is much larger than p. Increasing p, I decrease this denominator. This means if SSE is going to 0, is also this numerator is going to 0, is also going to 0 this denominator. This means it could be that I can find in a region of this R square adjusted, which is not monotonic with respect to n, and then can be used in the context of an optimization. Again, the principle. In any case, if I want to have a convex optimization problem, I need a global convex function. And also the constraint with this separability principle. You remember I told you separability principle. Now, if I change, if I want to optimize with respect to n, and if I want to optimize R square, I told you without demonstration that R square is not convex, is monotone with respect to n, it's not convex. Moreover, this constraint, I cannot separate this constraint, what I know with what I don't know. For two reasons, the problem is not convex. This means we say it's strongly not convex. The idea is at least to find in a region, not everywhere, with respect to n, in which at least the cost function remains convex. Even though the constraints remain the same, we cannot separate what I know with what I don't know, but it could be that I find some regions of R square adjusted with respect to n, which I have the convexity. I will tell you with the graph now what I intend. Let me conclude. At the end, the idea is to minimize both errors. Remember, we conclude probably here really flesh out. Which look at the expression on the right. Look at the expression on the right. The idea is to calculate the minimum of this expression. This means the minimum SSE with respect to theta, and that we did this together already. And the minimum of the whole expression with respect to n. The reason is, with this minimization, I will minimize, with respect to theta, the deterministic error. With the global minimization, I will minimize the SSR, because this is close to the SSR. It's a variation of SSR. Do you remember? This expression here is something like R square. We call it adjusted. This kind of formulation allows to say that at the end, I have an optimal theta vector, an optimal value n. They should be synchronized because n plus 1 is the number of parameter of theta, which minimize both errors. I think it's easy to show the example instead of many words. Here we have an explanation in terms of minimax. The reason is basically these two minima can be written as the minima with respect to n over square adjusted. Better to say in this form, the maximum with respect to theta of R adjusted and the minimum with respect to n. I don't know if you remember in the school or the analysis, subtle point. Auf Deutsch wäre Yeah. But can be seen probably better with two minima. Yeah, again, basically is what I told you exactly now, a little bit, just written. Try to look at home a little bit. Um, why in some region is the convex problem? Because in the subtle point, we have a minima and we have a maximum, just one. Don't mix the convexity with the convex function. And the convex optimization problem can be also defined in terms of max. Very important that one max. In a region, we have a local optimization, convex optimization problem. If I consider the whole domain, we have a global optimization problem. Convex could be also with a maximum, a convex optimization problem. I will coming back here with the PSO. Let me go ahead now with some example with MATLAB, heuristically, and then we will come back, I don't know, it could be the next week. I will start with PSO. PSO is an interesting method to be used in the context of non-convex optimization problems, but it's having the program. This means I will slow down a little bit because not everybody knows basic of programming probably. If while for loops, conceptually is very easy, but but I have programs that can be analyzed, I hope, together very well. Okay, MATLAB. Should I upload the file or I can do later? I can do also later, no? Or do you want to look together with me? Okay, let me upload. Just a second. Three courses. This is okay. This is exactly, yeah, no? Let me see what I have. Let me share also so you can. Okay, yeah, we have the. I can also upload here. I can also upload here. I think okay, because nevertheless, these files are related to the same lecture. I hope to find the right ones. I think it's three. Okay, let me go here inside. I come to you in a few seconds. I need this one, this one, this one, and this one, I think. 4 files. You can find now in this folder 4 files. Let me open the first one about MATLAB. I already told you last time. Let me open MATLAB. And let me share. I am opening MATLAB, no? Gesundheit. Okay, let me see. Is open. Let me share now. Yeah. Okay, you can see here. Let me go to the folder. I didn't repeat it, that we are in the window form or format of MATLAB. You can see from here the path, my path, where is complementary bachelor here, no? MATLAB exercise lecture 1 and 2. And you can see here, exactly. Let me open this one. Poly exercise 01, again, poly 1 r squared. Let me open, clicking twice, and you can see in the middle that we have this didactic exercise. Look, clear all means, do you remember we have seen also last time, in case we have variables already present in the kernel of MATLAB, in the defined, or better to say, in the workspace, no? Better to say in the workspace, we will cancel, no? We will cleared. Close means close all pictures, no? Just a prophylaxis, no? Because otherwise you will be full of pictures, no? The first one is a little bit of prophylaxis. You don't need really, but typically we do always. Look, X exploration vector. Last time I told a lot about that. You remember? Column vector. Intuitively, until here is the row, I realized the column with this apostrophe because I transpose the wire. The same for Y. Look, X1 is the exploration matrix. I have just 6 measurements, and then we have this column with 6 ones. This is the solution. You don't need to explain. Problem in the context of theta is convex, no? If n is given. Here, n is given from here. This is a comment, but it's clear, it's in a comment to say that I need an exploration matrix, which we have in a column of a vector x, and then another column with ones. I'm asking now, is this clear, this? Now it's clear. We have seen last time, no? This is the solution. Copy from the lecture. I insisted last time a lot. Now, here's just, the solution is already here. What I want to show you a little bit graphically, but I would like to show you how it changes R square, is how it changes R square adjusted, in order to understand a little bit better, a little bit the meaning. XS is a new vector between 0 and 30 with the resolution 0,02. Yeah, I can change this, but we can see in accordance with the value which I have. This means the step between 0 and 30 is 0,02. I mean, the first value is 0, the second value is 0,02, the third value is 0,04, and so on. The step. In order to represent in the best way, and remember, we have seen this, the value. Here's the regressor. N is fixed. I plot as last time. I plot also the measurement just to figure out what happens. Very important here. R squared. Yeah, here, and as in a comment, I put the definition. I would like to explain this. 1, no problems. And then we have to consider the sum, better to say SSE divided SST. Do you remember? SSE divided SST. And look, this here, I don't know if it's visible, is SSE in the language of MATLAB. Why that? Because we have the measurements, the vector, minus, let me look here because otherwise I don't see well. Yeah. Here's the vector, column vector. This here is also a column vector. Why that? Because X is a column vector. This means this here is the error vector, this orthogonal line which I told you today when I started. Then what I do, each element of this error, vertical error to understand, each squared. Remember the definition of SSE. Everything divided by this pseudo, let me say pseudo variance, the variations. Sum of what? The vector, the measurements, minus its mean value. Do you remember I told you at the beginning, think about in the basis of this y in the picture, y overlap. I didn't clarify it much, but now we can see this. Why? Because it's basically referred this SST to the y overlap. I mean, this SST equals SSR plus SSE works if the basic of the base of this vector is y hat, y overlap, y overlap. Each component up to square, up to 2, excuse me. Now, I put m equals 6 because it was exactly my number of measurements I told you before. N equal 1 because we want to simulate, you want to build this P equal N plus 1. And I copy R square, but in front, let me say, in front of SSE divided SST, I put this in accordance with the definition. Just in 1 second, I copy R square and I put this. Question here. Now we show you how to change R square, which takes into account, you remember, just the, let me say, optimization of with respect to theta. And then heuristically, I will show you increasing n, how we can see that R square adjusted will find the region in which R square adjusted is convex with respect to n, but R square is not sensible with respect to n. I mean, we will increase always. This means it's not for us a good parameter because cost function, better to say, to optimize everything with respect to n. Let me run. It's easy to tell to show you what I intend. Yeah, we have a graphical representation which does not tell much. It doesn't tell us. Good, bad. We cannot say anything because it's not quantitative. We can look, of course, but it's not in quantization of the solution. Please, homework. Please try to do at home everything using n equals 0. I didn't consider because typically we don't do n equals 0, but try to do it. Try to do at home. What to change? It's very easy. In your opinion, what I have to change for n equals 0? Should I do? Yes? Think 1 second. What I have to change for n equals 0 in your opinion? Let me do it, but think about. To do is this enough to save with another name, no? This is also a very important thing in programming. I worked in ABB, as in Brown Boveri, as control guy when I was young. I was involved in many projects with a lot of heavy programming hours, hard work. I remember that the software, we never waste the software. We modified the software. Very important is the concept. This means save with another name and do the modification. Also in your project. Each advancement, another name, another name. When a software works, store, save, and change the name. Here, I show you practically what I intend. Save as. No? We are in the right. In this sense, excuse me. Is this difficult? What I mean? It's easy because it's not true. It's just question. It's so. Also this year, this semester, I am invited for, I told you, for a lecture which takes just 10 minutes. The name is 10 Minutes Theology. I already told you, no? This time, the topic is the time. Huh? It's in the sentence of Sant'Agostino. Huh? If I don't think about the time, I know exactly what the time is. But if I think about the time, I don't know what the time is. And then they asked me to speak about the sentence and to speak about the cognitive part of the sentence. Then if I think about the time, what is? Also, the time does not exist, believe me. But not my sentence. It's the sentence of the most famous physics. In the modern physics, the time does not exist. Also, in our course, we will see the time. Everything is given. The time is given, but it's not in a state. It's given. Okay, we will see. Polynom 0, that makes sense, no? The new name. Exercise, I don't remember. Let me see the name here. Exercise 1, makes sense, no? Exercise 1, poly 0. Oh, why not? Let me save. Did you change already? What have to do? I accept, yeah, proposal.
It's n number of variables.
N is the order. Variables, I don't know what I intend, parameters.
Yes.
No, the number of parameters is n plus 1. You remember, it's easy to remember. Think of the line, high school. And the line is n equal 1, linear, but we have two parameters in the line, no?
Or 0%.
Look, I would like to show you what I intend.
Why? The plus one is the y percent.
Did you agree? Did you agree? If I consider n equals 0, I will just to calculate the constant, which I call, for instance, theta 0. N equals 0 means just one parameter, right?
N is 0. I don't have a function.
You have a function, it's a constant. You have a function of time, for instance, if the function of time, but it's a constant. The constant is the function. The function of time. I showed you. I show you what intent. It's exactly P of x equals theta 0. I have to calculate just this constant. I show you. Let me I know that for somebody is boring, but I see that not everybody. Ah, okay, now. Now the problem is I have a 6 measurements. I don't know where it is. No, I put very quickly now. I don't know where it is, but I have it. I plotted to now quickly. Otherwise, I am not able to go ahead. It is. Excuse me, theta 0. Huh? Ah, I want to do too fast. No? Where is must be calculated. What is the best value of theta 0, which approximate the measurements? I don't know. The program will say to us where is the level. Could be 1, could be 2, could be 3. I don't know. But this, what is the mean value? Do you remember I told you at the beginning? This is the mean value, which can be demonstrated, which is the mean value mathematically. This I leave you to your. If you want, I can do in an easy example. But let me show you what I intend now. What I have to change here? What I have to change in this matrix 1? In any case, it's 0 if you like. And then what I have to change here? Everything I can write. Did you like so quickly? Did you like what I'm writing? X1 equal x0, so I don't have to change anything later. It's clear? A little bit programming, no? What I have to change here in your opinion? We don't have x, no? I show you now very easy an example. It's unclear, no? It's unclear. It's clear. It's clear that I am looking for the mean value of the y. It's also known. Otherwise, I have an example very quickly with 2 values. What I do? In order to I can do also directly by hand, but if I find quickly, we can save time. I have it. I have it. Look, look, starting from here. The values are, let me take the values. Can I also here for you? You have 2 points. P1 x1 1 and y1 2. P2 is x2 2 and y2 3. I mean, if you like, in our notation, we have x1 2 1 2 and y2 3. We can use this notation or this notation. Until now, we use this. Look, y vector, circa, exploration matrix, wants to, exactly as I told you, we have a 6 ones. Now, in order to be quickly, multiply A0, which our unknown. You remember? This is the equation which, excuse me, this is the equation which we want to apply with the computer. If I have a many value, of course, directly, the computer calculates directly A0. Look here. What I did in order to show you what I intend. Y1 is 2, Y3 is 3. It's clear that this sentence here makes sense just if I write equal. Because the vector 2, 3 cannot be equals 1, 2 if I have just a parameter. I don't know if it's clear what I intend. Because I have two equations, but just one parameter. Yeah, I can say if I write equals, this means 2 equal A0, 3 equal A0. Does make sense. But with circa could have a meaning. Because you say, find an A, this vector more or less. No? I multiply on the left by x transposed, both equation. And then if you do row multiply column, 1 multiply 2 is 2, plus 1 multiply 3 is 3, 2 plus 3, equals, in order to calculate A0, now I have to calculate A0. This means this circa becomes an equal in order to calculate A0, which allows to say it's circa. What do you have here? 1 multiply 1 plus 1 multiply. We can see that is the mean value of Y1 and Y2. Mean value, everybody knows, no mean value. Okay, let me go ahead just to convince you. Run the program and look at R square and R square adjusted. Then we will go ahead quickly now. Okay. Okay, so. Okay, let's go. Look, run. What was? Okay, now I have to, I forgot to change something. Yeah, I forgot to change here. We don't have this. Because we have, in this case, just T1, no? Just one parameter. This can remain. This can remain here. I have to consider just one parameter. The regressor now is just T1. No? Oh, theta, excuse me. And I don't have to change anything here. Excuse me if I forgot to say I can cancel everything from here. No? Where is cancel here? Doesn't work. Okay, doesn't matter. Okay, let me see if now it's working. I changed. I show you what. No? I changed ys is just the unique parameter which I have. Theta is just one parameter. I can write theta. It's just one. It doesn't matter here, the index. It's redundant, the index. I can cancel if you want. Because we have just one parameter in theta. I told you exactly now many times. N equals 0. Then, of course, when you have ys, the regressor in the R squared is in a function of theta or the theta 1. The regressor in R squared adjusted is theta 1. Look at the results. We know this. You remember? R squared in case of a constant is 0. Theoretically, do you remember? Because we have the minimal statistical error, but the maximal deterministic one. It's in a situation we don't want, because in extreme situation, I mean, it's common experience when we say we have two extreme situations. Probably in the middle, we have an optimal solution to, auf Deutsch, zu wenig, zu viel. No? It could be that in the middle we have something better. It's an extreme situation. Zero statistic error, excuse me, zero, yes, statistic error, and the maximum, the minimal statistic error, excuse me, I'm tired. The minimal statistic error 0, and the maximal deterministic error in this sense. 1. R squared, in this case, is also not defined. This means we have something strange in the R squared. But this is strange because we have an error, and the error is here. No? We don't have m equal 1, but excuse me, n equal 1, but we have n equal 0. Therefore, I forgot also to update n. The case which we are considering now is not n equal 1. I forgot to update n. Let me run again. Both are 0. No? Yeah, the minimal statistical error, but the maximal. Now, let me run n equal 1. Open, we already had, no? N equal 1. N equal 1 is here, no? Poly 1. Now, let me run. Again, as I told you, we don't consider basically n equals 0 because in extreme situation, I calculate for you just to do an exercise, what changes, whatever to change. But we know that is in an extreme situation, in which we have the minimal statistical error, but the maximal deterministic one, the deterministic error. This means it's something which we don't want to have, this extreme situation. Look at this value. 0,98, 0,97. Now consider polynomial second order. We can see that the values are always the same. 0 order, which I did just to show you, but typically we don't do because we don't want an extreme situation. It's the values. This is the polynomial which we have to consider. Did you agree with the x1? Yeah, now we have seen last time a lot of about how we build the exploration matrix. The rest does not change. XS does not change. Here, please pay attention. I have to consider exactly the vector. No? Isn't a vector, but the polynomial expression. And then here at the end, again, for you, I copy the polynomial of the second order. We can see here with 3 parameters. I can write also ys, but I put directly everything in order to show you better. No, this is equal ys, but in order to show a little bit better. This is the same in R square and in the square adjusted. But of course, in the square adjusted, everything is multiplied by this correction factor. Look now what happens. Look, a square adjusted now is decreasing. Now we have a 0,07. Before, we had 0,9773. And here we have, instead of 77, we have a 73, smaller. Again, we don't accept n equals 0 because we know that's in a string case. What about r? R square is now 098, and we had for polynomial order 1, 9819, and then we have 9842. It's increasing. R square adjusted is decreasing. R square without adjusted is increasing. We knew that. Now let me look at the polynomial order 3. I don't know if it's clear what I am doing. I am trying to find the optimal with the method trial and error. I increase the n, I calculate the n corresponding theta, and I will look when R square adjusted is the minimum 1, but excluding, again, n equals 0. Let me now consider polynomial order 3. The values are, of course, the same, otherwise I cannot compare. Here we have the exploration matrix. Now we are able to build. Now look at the exploration matrix. Clear what I intend. Yeah. Question?
Ask where more important.
Yeah.
So when
We have also other metrics. It's not the unique one, but I am comparing R square with the square adjusted.
so if the function where n equals 1, but then plus 1, right?
Again?
The function where n equals 1.
N equal 1, yeah? No, n equal 1 is worse than n equal 2. Because we have an R square adjusted higher with n equal 1. I show you here what happens. I show, it's important to understand. N equals 0 is here, but we excluded directly this. We excluded this because this is nevertheless an extreme situation. It's an extreme situation. We cannot be considered because we have the maximal deterministic error, even though we have the minimal statistic one. We want to find the compromise, minimax. N equal 1, this is 0. N equal 1. N equal 1, we had, let me read. Is here, no? I think it's this 0,977, right? 0,977. It seems, right? I show you also R. R was 0,819. Zero comma 919, right? Is correct? Yeah. Going ahead now, we have seen polynomial second order. R square is increasing. We have here somewhere, it doesn't matter now if it's not, this is not really. 9, 8, 4, 2, no? It's increasing, we can see. Oh, excuse me. Yeah, I show you. 1 second. Um, I just copied. Let me show. I don't know if you see now. It's decreasing the square. This is not acceptable. I already clarified theoretically. It's decreasing. Look now, polynomial order 3. Let me run. This is the polynomial order 3. Now we understood how we can build the rest, no? I have to modify just a few points. Very important this year. But the rest, please pay attention basically as the regressor. And the regressor must be also in the definition of R square, square adjusted. You can write instead of everything ys. I put just for you to notice. Because this complex expression is ys. It's equals. Look, R square adjusted is decreasing again. 9, 6, 3, 1. Let me copy. Zero 0,9631 and R square is increasing because where is we have 0,9853, no? 0,9853. Now look what happens with the last test. Now, this I don't need to show anything. You know that what I intend, what we can do, where I can change. This is the comment, the polynomial. Let me run. I am concluding. We have R square adjusted is 0,9720. This means I am now increasing 720. And R square is again increasing asymptotically, but is increasing. I am concluding. Look. We have a minimum for R equal to, if I don't consider, of course, this is an extreme situation because I want not only to minimize the statistical error, I want to minimize both because our phenomenology consists of two errors. We cannot trust just to minimize one component of the reality. And we can see that in this didactical example, that we have a region of convexity with respect to n. For n equal 3. With this method, a heuristic method, I have to check. R square is not something which I can trust because nevertheless it's always increasing. This means I cannot find a compromise in between. Question. Who can say that probably later we have a better value than n equal 3? Nobody. It could be that we have a better value. But typically we consider the first one because it's also the cheapest one in terms of calculation load. The polynomial is short. This means typically we are satisfied, but nobody can say, no, God knows where the minimum is, the global minimum is. We will see that PSO, this could be also in a project with PSO, in such kind of problems, we don't need to test, to check moving many programs. One programs to look. Of course, also PSO does not find the truth, because the truth does not exist. Better to say exist, but Just God knows the truth, the global minimum. Okay, next week, I introduced just now the topic. We will see that considering this not convex problem, I can also choose not only the order of the polynomial, but I can choose also the family, the best family. The problem is connected. It's connected because what is the best family? The best family is the family which find the minimum of the SSR and the minimum of SSR with the minimal number of parameters. Because we optimize here, not n, of course, we optimize n, but we optimize p, the number of parameters. Now, let me show you just one slide. Even though I will upload in the presentation, we will see next week. Yeah. Oh, but is in a more structured way. Yeah. I have in the presentation. Don't be scared. Don't be scared. Don't be scared. I have in a presentation, then I have a simulations. I have a presentation, then I have a simulation at the end. Before simulate, I will show you also these calculations. But this is easy. And a combination sign, please don't be scared from math. You have from many information get the what is important here is the sum, as in polynomial, of sine and cosine, of sine and cosine. We will see, I have a structural lecture in which I can introduce a little bit, in which we can see, do you remember Fourier analysis? Probably you remember Fourier analysis. Fourier, no? You don't, Fourier, that is the basis of Fourier. In a combination of sine and cosine, in which we have a different, let me say, frequency. We can consider frequency or we can consider period, as you like. You remember the period characterizes the trigonometric function. We will see in detail. We can consider the sum of sine and cosine with different periods. Note the slide a little bit more easy. You will see some content. Look at these two trigonometric functions. They are two sine functions with two different periods. But don't scale because the computer is there to help us. If I have many sine, cosine, the computer does the calculation in nanoseconds. Very important to understand when we have two different periods. Two sine with two different periods, two cosine with two different, in order to understand the concept. If I have 100, we have the computer that helps us. It's in a combination in terms of sum, linear combination here, of two sine, just to understand the concept. I will tell you next time, and this I will sketch how we can choose between trigonometric function and polynomial function, but also you can consider exponential function. Now we have the criteria or criterion to choose between any kind of family. It's the family which minimizes as R square adjusted with the minimal number of parameters. Of course, it could be that we have a better R square adjusted for a larger number of parameters, but typically we don't look, we don't care about that because another goal is also to have a compact formulation, at least in engineering field, in which we have to run the approximation of some part of a system. Do you remember this hysteresis curve? Engineer understand me what I intend, the inductance and so on, in a very short time. This means also the regressor, also the function which approximate the hysteresis should be very compact. The few number of parameters means. This is the best family too, no? Between sine, cosine, between trigonometric and polynomial, between trigonometric, polynomial, exponential function, what we want to compare. When this function could be suitable? When we have in the data some periodicity, no? In any case, it seems to be that the deterministic error can be minimized with a few parameters in this sense. But also this is in a conjecture. The best way is to compare. Okay, let me stop the lecture here. Where is now here? No? Let me do polite. Thank you for your attention. We will see next week. I am in Hamburg in the first part of the day, but if I'm not able to come, or if I am able just to come a little bit later, I will communicate with you per email from. But I think it should work because I have in the morning. We will see. Thank you for your attention.